Power steering is easy to take for granted. You spin the steering wheel and your car turns, right? It's as simple as that. But behind the scenes, your power steering is making it easy. Think of it this way. You've got something to lift that's really heavy, maybe too heavy to lift on your own. But strap on your robo-arm, and bam, you're Schwarzenegger. Power steering is like that. Without it, it's really hard to turn your steering wheel. Not impossible, but really hard. Your power steering system assists your efforts, making steering easy and safe. Now, the vast majority of vehicles on the road have hydraulic power steering systems, which means that pressurized fluid is used to help you do the work of steering. Get this, a pump pressurizes the power steering fluid to provide the boost you need.
Steering a heavy vehicle by manual effort only emphasized the need for a steering assist. This has been accomplished by adding a hydraulic system to the cam and lever steering mechanism. In this film, we will discuss the principles of operation of the hydraulic steering system. To obtain the assist, a hydraulic system has been added to the cam and lever mechanism. The hydraulic steering system is made up of 5 major components: the reservoir, pump, relief valve, control valve, and power cylinder. These components operate on the principle of pressure differential. Pressure differential is illustrated by this section of pipe. In the pipe is a movable block. The arrows on either side of the block represent equalized pressure. As pressure on one side of the block is increased, a pressure imbalance or differential is created in the pipe, moving the block in the direction of the lower pressure. The moment the pressure on the opposite side of the block is increased to equalize the pushing force, the motion of the block is stopped. In like manner, as the fluid pressure is increased on one side of the piston will be moved by pressure differential, aiding in steering the front wheels through the steering linkage. To aid in illustrating the internal function of the hydraulic system, a schematic diagram will be used. The steering linkage from the Pitman arm lever to the front wheels will not be shown. Let us view the 5 major components of the hydraulic system as they operate progressively to deliver the steering assist. The reservoir supplies fluid. The pump, driven by the engine, delivers the fluid under pressure to the relief valve and control valve. The control valve, actuated by the steering shaft, directs the fluid to the power cylinder. The power cylinder converts hydraulic pressure into mechanical force by means of a piston. The control valve is the heart of the hydraulic steering system. The control valve has a spool which directs and controls the flow of fluid to the power cylinder.
The most widely used hydraulic shock absorber is the direct-acting telescopic type. It can be fitted as a self-contained unit or combined with a suspension strut. The strut type uses the same principle of operation, but it is considerably larger. The hydraulic shock absorber provides its dampening action by transferring oil under pressure through valves which restrict the oil flow. The twin tube type is the most common. The outer tube is normally attached to the suspension member at its base, and the inner tube provides a working cylinder for a piston which is attached to a piston rod. The piston rod is connected to the frame at its outer end, and a bearing at the top of the outer tube keeps the rod in alignment as it moves in and out of the shock absorber with suspension action. A seal above the bearing prevents oil leakage and keeps out dirt and moisture. A shroud protects the rod from damage. During bumps or compression, the rod and its piston move into the shock absorber. In rebound or extension, the rod and piston move out of the shock absorber. For dampening to be effective, resistance is needed in both directions. This is provided by the oil and by disc valves attached to the piston and the base of the inner tube. Oil fills the inner tube and surrounds its outer surface to a level which allows a free space or reservoir to exist above it, between the inner and outer tubes. On bump or compression, the piston and rod move downwards in the cylinder, resulting in a small pressure drop in the chamber labeled A above the piston. At the same time, the volume of the chamber labeled B below the piston is reduced, causing a high fluid pressure. This unseats the piston intake valve, and fluid flows up through the outer passages in the piston and into chamber A. But the piston rod is also now entering A and displacing a quantity of fluid equal to its volume, so all of the oil in B cannot flow into A. The displaced fluid is forced down through a base valve and out into the reservoir labeled C. In the rebound or extension phase, the piston and rod move upwards and the volume of chamber A is reduced. Chamber A becomes a high-pressure area, and fluid flows through the extension valve in the piston into chamber B. However, the withdrawal of the piston from B greatly increases its volume, and fluid flow from A is insufficient to fill the space. Pressure in B falls below that of the reservoir, causing the base intake valve to be unseated. Fluid flows from the reservoir into chamber B, keeping the inner tube full. The valve provides control over the amount of force required to pass fluid through them at any given piston velocity. They can be made to open in stages, according to fluid pressure. This allows light resistance to motion when the piston moves slowly, and heavy resistance when piston velocity is high. The rapid movement of the piston, continually forcing the oil backwards and forwards through the valves, causes it to heat up, as it absorbs the energy of motion of the spring and converts it into heat. The heat is transferred through the outer tube to the outside air. However, the hotter the oil becomes, the greater its tendency to aerate. Aeration occurs because of the high velocity of the oil as it passes through the small passages in the valves. If the velocity is high enough, air dissolved in the oil comes out of the solution as small bubbles and forms a foam. Aerated oil has a certain amount of compressibility, so it is unable to provide the dampening force previously achieved in the non-aerated condition. The performance of the shock absorber is thus considerably reduced. This effect is called shock absorber fade.
The theory of hydraulics is this. Force that is applied at one point is transmitted to another point using an incompressible fluid. In other words, hydraulics is used to increase force and torque. In the case of brakes, this increased force is used to apply friction to the rotors and drums to slow the vehicle. Here's how hydraulics work in the car's braking system. When the pedal is pressed, leverage multiplies the force applied from the pedal to a vacuum booster. The booster multiplies the force again and actuates two pistons inside the master cylinder. As the pistons are pushed forward, piston seals operate against a smooth bore to generate hydraulic pressure. This rise in hydraulic pressure is transferred through steel lines and brake hoses to the four wheels. We said inside the master cylinder there are two pistons. Simply put, the primary piston serves the front two wheels and the secondary piston works the back two wheels. The master cylinder was designed this way for safety reasons. If one of the piston seals develops a leak and fails to generate enough pressure, the other piston supplying hydraulic pressure to its two wheels will be able to stop the car, provided there's no leak there, too. It's this pressure that activates the wheel cylinders and/or disc brake calipers at each of the four wheels to initiate the braking process. The neat thing about hydraulic systems is that the steel piping and brake hose that connects the master cylinder to either the wheel cylinders or calipers can be of any length and shape, since the same amount of force generated at the origin arrives at the destination. As we were talking about hydraulics, incompressible fluid is the agent that transfers power generated from the master cylinder to the four wheels. Brake fluid is usually a glycol-based formulation, which is a similar base formulation to antifreeze. The fluid is also used to lubricate components and needs to withstand cold temperatures so it won't thicken and hot temperatures so it won't boil. If temperatures do rise enough to bring the brake fluid to a boil, it results in a spongy pedal.